Well, greetings, mathletes, and welcome. Um, so today we're going to be talking about slope. I know it seems like it's an Algebra 1 topic. In Algebra 1, what you were talking about was the slope of a line, right? But we're going to be applying this idea to functions in general. And we're actually going to be looking at it in two different ways. And so the way this lecture is going to proceed, I'm going to start by showing you what the theoretical, the concept is behind what we're doing. And then once we get through that display, we'll go in and get our hands dirty and actually start playing around with what that means for the mathematics when we're doing this stuff algebraically. Okay, so without further ado, this is the demonstration. So I want to show you a couple of things, make you aware of a couple of things. So we have x coordinates down here, right? I have x1, x2, and then I have this distance here between x1 and x2, and that's traditionally called h. Okay. Now, so the idea here is, excuse me, the idea here is to be able to find the slope between any 2 points on a function, right? And so if you move these points around, clearly this line here, it has a slope, right? And as these points move around, it changes, right? You can see this distance changes. So really what we're going to be doing is altering the distance between some point that we're interested in and a second point. Okay, so ultimately where this is going is we want to know what the slope of the tangent line is right here at this point I have marked A, right? So to get a hold of that, what we do is, whoop, try that again. Why are they both moving? There we go. What we're going to do is basically we're going to slide these values together. And if you notice, as these 2 points get together, as this distance gets smaller, or as we're going to say later, as h goes to 0, it starts getting closer and closer to the actual slope of the line at that point. Now, once you hit that point, well, this isn't actually hitting the point. It's technically undefined because the change in x is 0. But yeah, that's the idea. Is we're gonna have a way of getting these guys closer and closer together until we know the exact value of the slope at the point A. Right? That's what we're actually after. Um, but in the meantime, there's some other things that are kind of nice. For instance, this line right here between these 2 points, right, between this point on the function and this point on the function, the slope of this line is actually the average slope for everything in between it, right? It's this total change in y over this total change in x. And so what we're going to be doing is taking a look at that. And there's actually more than one way to get a hold of this. And so we're going to be looking at more than one way. But all of this actually is born out of the slope formula. So we're going to take a look at that and go from there. All right, so that's the demonstration, and we might reference it again here. I don't know if we will or not, but let's actually get to the mathematics. Okay, so I went ahead and copied and pasted the picture over so we could look at it for reference. But let's say we are trying to find the slope. Why didn't that write? Oh, because I don't have the pen on. Between these 2 points, right? Now, we don't have any exact coordinates on these things. I didn't even point out what the function actually was. So we're going to do this entire thing completely symbolically. And we're going to start with the definition of slope. Ooh, let's make this a little smaller. Okay. There we go. Thinner. So the definition of slope is the change in y over the change in x. Right? Now, if you haven't seen this before, these little triangles here are the Greek letter delta, and they are triangles. They're just little equilateral triangles. It's the Greek letter delta, and it stands for a change in something. The reason that the Greek letter delta was used is because D is for difference, right? And that word is very similar in other languages as well. So the change in y is actually y2 minus y1. over x2 minus x1, right? The traditional slope formula. And we already have x1 and x2 right here, right? Now notice that means, what that means is the change in x is the difference between the two x values, and the change in y is the difference between the two y values. Okay, well, if we think about how we went about finding those y values, we would have plugged the x values into the function to figure out what they were. So that means that y2 is f of x2, and y1 is f of x1. Okay, so we're going to substitute those in. So those things give me that this slope is now f of x2 minus f of x1 over x2 minus x1. Okay, now the average rate of change, the instantaneous rate of change, right, can be computed using this formula. Or, excuse me, not the instantaneous, the average rate of change over an interval, right? So, so the rate of change of x, well, or I should say of f, the function, over the interval from x1 to x2, is this formula, right? So that is f of x2, I'm having a hard time with writing here, f of x2 minus f of x1 over x2 minus x1. Okay, now, this works over an interval, but we actually have to do this a little bit differently if we want to find out what the rate of change is at a particular point, right? What the slope of that tangent line actually is, right? That's when we take this point and slide it over to this one, so to speak, right? Or rather, it's kind of like taking x2 and sliding it towards x1 is what it is. Well, you notice we already have a label for that distance there. x2 minus x1 has to be h. So if h is equal to x2 minus x1, let me switch colors just so it stands out. There's two things that happen. One, well, that denominator becomes an h then, doesn't it? Right? That's no problem at all. But the other thing is I can now, if I add x1 to the other side, I have that x2 is equal to x1 plus h, right? So we can actually rewrite our entire formula using these two things for, let's see here. So x2 is x1 plus h. So this is f of, now it's not x2 anymore, it's x1 plus h minus f of x1, and this is all over h. Okay, so this is our other formula. Right, the first one's used if you want to find the slope between 2 points on a function. This one we're going to use, and we'll see how to use it. We actually have to do a little bit of imagination because we haven't defined some things yet. It's actually not till the next section. But this is one to find instantaneous. To find my handwriting. And the problem we end up running into with this guy is that if we want to know what the value is at the point, this distance right here, right, that means I let this point go all the way till it falls on top of this other one. And that means that h is 0. And that means we're dividing by 0. And so we have to find a way around that. And that's really what that's what a lot of calculus really is. It's just, it's not that the idea of finding a slope is difficult. It's that functions aren't always cooperative, right? There's a lot of algebra involved in figuring out what these things have to be. And usually that algebra somehow involves trying to eliminate h from this denominator. And that's what we're going to be after. As far as the algebra goes, that's going to be where the challenge is going to fall in, because you have to be kind of creative sometimes. Okay, so let's go ahead and clear this off, and we will take a look at an actual physical, well, maybe not physical, but more tactile example. Okay, so let's say we want to find the average rate of change over the given interval. Okay, so that's what we're finding. The function we're given, let's see, f of x is equal to x cubed plus 1. And the point we are looking at is the point 2, 3. Or excuse me, not the point, the interval we're looking at. I can talk, I swear. But yeah, the interval we're looking at is from 2 to 3. Okay, so that means that those are x values. So the x values are 2 and 3, and we're looking for the slope from the point where x equals 2 to the point x equals 3. Well, what we know, we need to find our delta y and our delta x, right? Not too bad. And we know that is f of x2 minus f of x1 over x2 minus x1. Well, the x2 and x1 aren't too bad. This is x1 and this is x2, so those are going to be easy to plug in, right? What we need is f of x2 and f of x1. Well, even that's not too bad. All we have to do is take these and plug them into the function. So f of x2 would be f of 3 right? And f of 3, well, 3 cubed is 27 plus 1 is 28. Okay, and then f of x1 would be f of 2. 2 cubed is 8 plus 1 is 9. Right? So we can plug all this stuff in now. Let's see here. So we get f of x2, let's see here, that's 28, minus f of x1, which is 9, and then x2 minus x1, which is 3 minus 2, right? Okay, well, 28 minus 9 is 19, and 3 minus 2 is 1, and so over the course of that interval, the slope is 19, right? It does help a little bit if you can picture this. I mean, really what we're looking at is we're looking at a cubic function. That's a pretty steep slope, right? You don't usually see that when you're graphing lines. And this guy goes up this way. And so really what we're doing is picking like 2 and then 3, and you can see it's pretty steep. And this probably isn't a drawing that shows how steep it actually is. But you can see that this tangent line here is going to be pretty steep when you look at it. So, and cubed functions get steep real fast. But that's what we just found. We just found that interval over that single x value, right, from 2 to 3, that's 1 unit. We found the average slope over that unit. Okay, so let's go ahead and take a look at the next one. Okay, so let's make this one, you'll recognize the function, but in this context with the idea of slope, you usually don't see these things, at least not until this point. Let's make, oh yeah, I have to do that whole turn on the pen thing. Let's say f of theta is equal to cosine theta. And the interval we want to look at this on is from 0 to pi. I keep doing that. Wrong bracket. There we go. Okay. Now, if we think about what this looks like, right, the cosine curve goes down this way. Let's try that again. Let me see if I can get a better angle on this thing. Oh my goodness. One more try. Right? Cosine curve looks something like that. Sorry, it took so long to draw it. 0 would be here, pi is here. Right? So what we're looking for, if we want to map it out, here's 0. So the point I'm starting at is up here at 0. And then at pi, I'm right there. So we're looking for the slope of this line right here. Right? And that line will give us the average slope over that interval. Okay, so let's do this. Again, we're looking for change in y over change in x. Right? And so that's going to be f of x. Oh, it won't be x this time. F of theta 2 minus f of theta 1 over, well, let's write it correctly, theta 2 minus theta 1. Right? So that's what we're looking at. Okay, so we just need to compute these things. So I need f of 0, which is cosine 0. And cosine of 0, we can actually just see it from here as 1. Right? And then I need f of pi, right? That's f of x2. And if we look at here, we can remember that cosine pi is -1. Okay, so that makes things a little bit nicer. Now we can start playing with this stuff. Let's see what we can get. Excuse me. Okay, so that means we need f of theta 2 minus f of theta 1. So that's -1 minus 1, right? And then we need to put that over theta 2 minus theta 1, so pi minus 0. So if I have pi minus 0, well, that's just pi, and -1 minus 1 is -2, so this ends up being -2 over pi as the average slope on that interval. So you can start getting used to seeing weird things pop up. You've probably never seen pi show up in a slope before. It's gonna continue to do so. So just be aware of that. But you notice what we're doing is still just computing the slope. That's all we're doing. This is basically a slope formula rewritten in a different fashion. All right. Well, I think that'll cover you as far as the average rates of change over an interval, right? The idea is you just need to be able to compute the function values at both ends, and then find their difference, and then find the difference of the x values, and you're taking their quotient after that, right? So it's really just the slope formula, change in y over change in x. Okay, so let's go ahead and look at some instantaneous rates of change. So let's go ahead and clear that out. Okay, so let's suppose we want to find, oh yeah, I still have to turn that pen on. We want to find the instantaneous rate of change. Right? So this is at a point. At point, and we'll call it P. Since that's what your homework calls it, I'll just call it P as well. So this is how the problem is presented to you. So you're given a function, y is equal to 7 minus x squared. Right? And you're given a point. These things are often separated by a semicolon. Right? And the point is 2 3. Okay, so one, it does help if you can sketch a picture of this, right? So really what you're looking at is you're looking at a parabola. 7 minus x squared would be have a y-intercept of 7 and do something like this. I'm just doing a sketch. I'm not even going to put numbers in here. Um, but from 2 to 3, I can see this thing is going down, or not from 2 to 3, at the point 2, 3. So let's just say that's there. We're going to be we're basically looking for the slope at this particular tangent line, right? We're looking for the slope of that tangent line. Then once we find the slope of that tangent line, we're going to find the equation of the tangent line, right? So we have to remember how to find the equation of lines as well. But by the time we're done, we're going to have a slope, and here's our point. And you know you can always find the equation of a line with a slope and a point. So let's go ahead and check this out now. Now remember, if we're finding the instantaneous rate of change, we're not using f of x2 minus f of x1. We're using that substitution with h to turn the whole business into f of x1 plus h. And by the way, oftentimes that 1 is just dropped since we're now down to one variable. But I'll keep it for the time being. Minus f of x1 over h, right? So that's what we're trying to simplify. Right, so we have our f of x1 here now. And so that's going to be, or excuse me, we have x1 here. This 3 is f of x1. That, let's try that again. I don't know what I just did. There we go. That 3 is f of x1. Right, that's what we're looking at. So so we already have that value. This is going to be f of 2, and this is going to be f of 2 plus h. And so let's go ahead and take a look at what the mathematics looks like on this. So we have, since x1 is 2, this is f of 2 plus h minus f of 2 over h. Okay, that's what we're looking for. This is our delta y over delta x. Okay, well we have functions that describe these things. We're not going to have to deal so much with the f of 2 because we know that's equal to 3. That's actually given to us already. But let's see here. F of 2 plus h will be 7 minus 2 plus h squared. And then f of 2 is 3. So this is minus 3. And the whole business is over h. Right? Again, we need to simplify this thing down because really our goal right now is to get h to make h 0. Now I do want to hedge this a little bit. In the next lesson, we're going to have a much more formal way of getting a hold of these things. But for right now, it's essentially the same as plugging in 0 for h. What do you call it? This is only working because the only thing you're being given are continuous functions. So there's other cases. Just be aware of that. But for right now, we want to think about it as it's essentially plugging in 0 for h. The problem is it's going to make us divide by 0, right? So what we need to do is figure out how we can simplify this thing down so I'm not dividing by 0. So we're going to expand this whole thing. So we'll go to the next line here. This is 7 minus, and I'm just going to go ahead and multiply this out in my head and then multiply the negative end. You guys can fill in the algebra in between on that. So this would be, let's see, that'd be 4 minus 4 minus 4h minus h squared minus 3, right? The minus 3 comes from here. And we'll divide the entire thing by h. Now if we simplify, 7 minus 4 is 3, minus 3 is 0. So these guys go away, right? I don't have to worry about that now. I'm down to You're going to have to excuse my panicking cat here. She wants out the door, but I'm going to finish this problem first. So this is minus 4h minus h squared over h. And you notice h is a common factor in the numerator. So this makes this negative 4 minus h over h. And now we can cancel this out. So now I have negative 4 minus h. And if we let h equal 0 here, the answer is negative 4. Okay, so what that means is that the slope at the point 2, 3 is negative 4. So the slope of this line right here is negative 4, which is actually kind of cool that we can narrow that down. We can actually find the slope of a tangent line. Okay, so we got through that. Now let's find the actual equation of the tangent line. So we know the slope. I'm just going to write it down. M equals negative 4. And we're going to go ahead and let's do this. Where's the select button? Let's see if I can get all this stuff off here in one fell swoop. That's most of it. All right. Well, you notice we have a slope and a point. This basically reduces our entire problem to find the equation of the line with a slope of negative 4 that passes through the point 2, 3. Now, there's a number of ways to do this. Most of the time, I just like to do it this way. You're welcome to use the point slope formula or anything like that too, but this is how I usually do it. I know I want y equals mx plus b, and I have m, so this is now y equals negative 4x plus b. And if I just need to find b, well, I have an x and a y right here, 2 and 3, right? That's x, that's y. So I can plug those in here. So 3 is equal to negative 4 times 2 plus b. And so that means 3 is equal to negative 8 plus b. And that means 11 is b. And so if 11 is b, all I have to do is plug it back in here. The tangent line at this point is y equals negative 4x plus 11. Right? That's adding this to the mix. Right? So this is the line that we found the slope of. Right? That's this line. And that means it crosses up here at negative 11, or positive 11. Excuse me, I said that backwards. Okay, so let's just kind of review what we did. Okay, we needed to find the instantaneous slope. So we used this formula, right? We know what x is, and we know what f of x is. And we know what the function is. So what we end up doing is computing this numerator and then massaging it algebraically so that we can eliminate h. Right? That's the goal. You're always trying to eliminate h out of the denominator because you don't want zeros in the denominator. And you're ultimately going to be looking at h as a 0. I really feel like I have to say this again. Technically, it's approaching 0, but we haven't talked about what a limit is yet. So once we found that, right, once we had simplified that and got rid of h in the denominator, we just kind of plugged in h for, or plugged in 0 for h to see what the value ends up coming out to. We found the slope then. Then we took that slope and the point that we were given, and we found the equation of the line, right? So again, you notice nothing we're really doing is all that different from an algebra class. It's lots of little pieces from all over the place that we're just taking and putting together into one idea. Okay, so having walked through our first example of an instantaneous slope, let's look at a second example here. So let me go ahead and, oh, that is not selecting everything. Let's just do it that way. Yeah, let's go ahead and take a look at another example here. Now, with the polynomial equations, one of the things that that happens quite frequently is what you just saw. It boils down to multiplying everything out in the numerator, collecting like terms, and then factoring out an h, and you can go ahead and eliminate h using that. Now, other functions are, at the very least, more interesting. So let's take a look at this one here. Let's say I have what, didn't I, there it is, y equals the square root of x, and the point is 4, 2. Now, what I want you to do right now, because we are looking for the instantaneous rate of change at a point, I want you to go ahead and try this one, and then you're going to notice some sticking points. But I want you to be aware of the sticking points before you watch the solution. Maybe you can barrel right through it, and it's not a problem for you. But go ahead and pause it here and see if you can find the instantaneous rate of change at that point. And then once you have worked that out, check your, or if you get stuck, push play again and check your answer, or see where you're running into trouble. Okay, so pause here. Did you pause it? I'm looking. Okay, so let's go ahead and take a look at this. Let's see here. So again, we want to use, and I don't think I actually gave this the proper name too. This is called the difference quotient. Right? The difference quotient is f of x1 plus h minus f of x1 over h. Right? That's our difference quotient. So let's see if we can fill this out. Remember, this is x1 and f of x1. Right? So we have that computed already. In fact, you can even check. If you plug this x in here, you get that y value. Okay? So what we end up with is, I'll write it here, the square root, let's see, x is 4, of 4 plus h minus the square root of 4 over h, right? And that is what we are trying to simplify. And you can see the problem already. There's nothing to multiply out in the numerator. There's really not much to do here. The square root of 4 is 2, so we could simplify that. But again, we're back where we started. I can't eliminate that h like that. So here's what we end up doing. I would kind of wish I had started over here. I wonder if I can do this. Let's see if I can move this. Oh, I can. Perfect. Okay. So here's what we end up doing. And this is where the idea of a conjugate comes in. If you remember, when you're dealing with roots, there's a conjugate. And we used to use them for rationalizing the denominator. Some teachers like to go through rationalizing the numerator as well. And that's actually what we're going to be doing. So what we need to do here is take the numerator and the denominator and multiply it by the conjugate of this expression. And the conjugate of this expression is this expression with the minus turned to a plus, or if it was a plus, you would turn it to a minus. Because what it does is it gives you the difference of squares. Right? And we have to do the same thing down here. Okay, so far so good. Now, let's see here. If I multiply these, and remember the difference of squares, all you have to do is square the first term, square the last term, and then subtract them. So if I square the first term, that's 4 plus h, right? No root. Squaring the last term gives me a minus 4. And then in the denominator, I have h times the square root of 4 plus h minus 2, right? Okay, well, let's go a little further here. Let's see what we can get with this. Excuse me, plus 2. Boy, that would have been a problem. We would have been dividing by 0 anyways if I just made that mistake. Okay, 4 minus 4 goes away, and what I end up with is h over h times the square root of 4 plus h plus 2. Right? H is cancel, and that means I have a 1 in the numerator. And if I look at this expression now, and I go ahead and let h equal 0, that means I'm taking the square root of 4, which makes this a 2, right? So I have 1 over 2 plus 2, which is 1 over 4. And so our slope is 1 over 4, right, at that particular point, at the point 4, 2. The slope is 1/4. It's kind of cool, actually. Now, we found the slope. What we need to do now is come back over to our point and find the equation, right? So this is our instantaneous rate of change at the point P. We need let's go ahead and do this. We need to find the equation of the line. So I'm going to go ahead and get rid of some of this here. Let's go ahead and delete that, and then we'll delete that, and just erase that. Okay, so we know we have our point, we need a slope, we have 1/4 as a slope, so that means I know my line's going to start out with y equals 1/4 x plus b, and I just need to plug in the point 4, 2. So that means that 2 is equal to 1/4 of 4 plus b. Well, 1/4 of 4 is 1, so 2 is equal to 1 plus b, and so 1 equals b. And I can take that back up to my equation, and the equation of the line now is y equals 1/4 x plus 1. Right? So that's a good clean fun right there. Okay, so we found the instantaneous rate of change, and then we found the actual equation of the slope of the tangent line. Right, that tangent line actually ends up being fairly important in the long run. Finding the tangent line at a point, in this particular case, we're talking about a square root function, and we found out that at 4, wherever 4 ends up, I have this line, right? It's with a slope of 1/4. Because of the fact that there's a region where the line stays fairly close to the function itself. And so these lines are quite often used as estimators. It's one of those things, especially what they call numerical analysis. The equation of a line is used quite often. So we're going to be seeing plenty of it this semester. Okay, but nonetheless, there's the equation of the line, and there's the slope at that point. That's the instantaneous rate of change at that point. All right. So let's look at one more, and I think that'll take care of most of the cases that you're going to see, the different types of functions. I want you to try this one on your own also. So you saw the little trick with using the conjugate. So this time, let's let f of x equal, I have it here, 1 over x, and the point P is the point -2, -1/2, right? So that's what we're dealing with here. The point -2, -1/2. Let's see if we can both find the instantaneous rate of change and the equation of the tangent line. Okay, the tangent line shouldn't be too bad because, once you have the slope, it's all downhill. That's a slope joke, I guess. Anyways, pause it here and try. Okay, so I'm assuming you've paused it at this point. Let's go ahead and dive headlong into this. So we want to start by finding the instantaneous rate of change at the point -2, -1/2. So that's, again, it's going to be change in y over change in x. And I'm just going to go ahead and drop the subscript this time. This is f of x plus h minus f of x over h, right? We know x is -2. So this is now f of negative 2 plus h minus f of negative 2 over h. Okay, if we go to the next line here, we're just going to go ahead and use the function now. This is 1 over negative 2 plus h. And it'd be minus negative 1/2, so it's plus 1/2 over h. All right, so now we have, well, this h won't cause a problem because if I make this one 0, it's just negative 1/2, right? But I'm still dividing by this h, which is a 0, right? That'll make the whole denominator 0. So the question is, what can we do about it? And I know what I like to do is just clear out these denominators in the numerator. If you have a fraction, you're allowed to multiply the numerator and denominator of a fraction by the same number. Well, this is the numerator and this is the denominator. So what I'm going to do is multiply top and bottom by this the common denominator of the numerator. So now this is, let's see here, it'd be the common denominator. Let me get this out of the way. Would be, let's see, there has to be a 2 in it, and there has to be minus 2 plus h in it. All right, so that means we do the same thing to the bottom. Okay, so let's see what happens. So here, this will cancel this guy and leave this as a 2. Right, so this ends up canceling and becoming 2. Over here, the 2's cancel, and I'm left with minus 2 plus h. And this whole thing is over this denominator, which would be, if I just simplify it a little bit, 2h times negative 2 plus h. Okay, well, you notice in the numerator, 2 minus 2 is 0. That goes away. And then what that means, I'm left with h over 2h times minus 2 plus h. Well, the h's cancel, and that leaves me with a 1 in the numerator. So now I'm here. I have 1 over 2 times negative 2 plus h. Okay, well, if we're letting h go to 0, and by the way, this is the notation for that. If we let h go to 0, what happens is I get 1 over negative 4 as my slope. Right, so now I have a slope. And you notice the big key on that one was to multiply everybody by the common denominator. Right, so there's little algebraic tricks that are going to be popping up throughout these problems. And when we start doing trig functions too, it's one of those things where you need to know your identities so that you can manipulate these things so that you can simplify them in the first place. That's actually going to be a big deal. Okay, so now we have that. We know our slope is negative 1/4. What we need to do is find the equation of the tangent line. So let's go ahead and get rid of some of this stuff now so I have room. We'll just do this. And then we'll move this one. I'll just put this over here. Boy, I'm sure glad I found out I could do that. That saves me so much trouble. Okay, so again, oh yeah. Y equals mx plus b. We know m is negative 1/4. And now we have an x, right? This is our x, this is our y, or we have a point, I should say. So what that means, and I'll just do this over here, negative 1/2 is equal to negative 1/4 times negative 2 plus b. Right, not so bad so far. Let's see here. Negative 1/4 times negative 1/2. That's going to give me positive 1/2. So I have negative 1/2 is equal to 1/2 plus b. And if I subtract the 1/2 over, I get negative 1. So b is negative 1. And all we have to do is plug it back in. Y is equal to negative 1/4 x minus 1. Right? And so now we found it. Now, Those are the examples I wanted to go through, but I wanted to point out a couple of other things that are going to be important. Um, One is that when you're looking at an instantaneous rate of change, okay, technically that is what's called a derivative. That's actually what the first half of the semester is about, is finding derivatives. Um, so let's see here. Where it gets applied is it gets applied in physics quite often, right? It turns out that, let me just clear this whole thing off. Well, let's try this again. There. It turns out that if you have some function that describes a position, right? Um, like a falling body, right? So let's say f of x was a height, right? Oh, geez. One of these days I'm going to remember to turn my pen on when I'm supposed to, right? It's a height over time where you can find its position. Um, if this is, oh, I can't spell. It's the height of a falling body. I can't spell anything right now. There we go. If h of t is height of a falling body at time t, then the instantaneous rate of change is the velocity, right? So the velocity is the instantaneous rate of change of some position. Well, you'll know exactly why I'm using height as an example once you start reading into the lesson. But that's one of the things you want to be thinking about. That velocity is a change in position, right? If you think about, because a change in position is a distance, if you divide a distance by a time, right, that means that delta H is a distance. It's a change in height. If I uh, if I divide that by the change in time, that is a distance divided by a time, which is a velocity. Oop, right? That's a velocity. So, in any case, I want you to remember that because this is going to keep on coming up. This relationship between physics and calculus. Calculus was invented for physics, so it's one of those things that it's going to keep coming up. In any case, that's everything I wanted to talk to you about today. So until next time, keep your pencils and your wits sharp.